Muscles are used in all types of sport and exercise. The forces necessary to run, cycle, throw, hit, jump and kick are all generated by contraction of skeletal muscle. But how does the human body bring about these contractions? All begin as electrical activity in the nervous system. Tiny electrical impulses, which carry the message to contract, are transmitted along motor nerves towards the muscle. When a nerve impulse arrives at a nerve ending, this message is passed on, and electrical activity then spreads across the muscle fibres. It is this excitation which tells the muscle to contract. A nerve impulse causes a synchronous contraction in a number, sometimes thousands of muscle fibres. Together, a motor nerve and all of the fibres it controls is termed a motor unit, with each muscle having many motor units, all firing multiple times per second. As sport and exercise scientists, we may be interested in measuring this activity, and this can be done using a technique known as Elektromiografija, or EMG. EMG can be recorded by inserting electrodes into the muscle, or alternatively, using electrodes placed on the surface of the skin which listen in. One is usually called the reference electrode. It's called this because the muscle activity is measured with reference to the activity here. Therefore, it doesn't want to be placed on a muscle, but over a bony landmark, such as the wrist. The other two electrodes are placed over the belly of the muscle, in line with the muscle fibre. The electrodes and wires are now in place to record from Paul's biceps muscle. However, there are other sources of electrical noise all around us. Power lines in the walls and ceilings, fluorescent lights and other pieces of electrical equipment all give out an electrical signal. Whatever the source of this noise, it's also picked up by our electrodes. However, this problem can be overcome by using differential recording. Suppose Paul and I went to a football match with the aim of recording the crowd. If I sat in one area of the stadium and Paul in another, the sound of the crowd in the area immediately surrounding us would be slightly different. But other noises, such as the public address system, the referee's whistle, or even a plane flying overhead, will be heard simultaneously by both of us. Therefore, by taking the differential, that is, by subtracting what I hear from what Paul hears, we'll be able to eliminate these common sources of sound. This can also be applied to EMG. As electrical noise is simultaneously picked up by both electrodes, it can be cancelled by looking at the differential. However, as the two electrodes pick up slightly different versions of muscle activity, this is not removed. This process is carried out by the amplifier, which also amplifies and filters the signal, before passing it on to the data acquisition card, which digitises the signal for it to be stored on the computer. Here on the screen, I'm showing Paul's biceps EMG. At the moment, the line is flat, and that shows that his arm is relaxed and no motor units are firing. However, as soon as Paul makes a movement with his arm, you can see that an EMG trace appears. This shows that motor units are firing in order to generate that force. Now, if Paul holds a small weight and repeats the same action, the EMG amplitude is larger, indicating that more motor units are firing. And if we replace that weight with an even bigger weight, the EMG trace is larger still. Remember, this shows motor units firing and the electrical activity spreading across the muscle. So here, more motor units are being recruited in order to generate the extra force. EMG data is usually processed by firstly rectifying the raw data. This involved taking the absolute value of the data points and can be seen on the middle graph, where all of the data is above zero. Filtering is also often used to smooth the signal. As shown in the lower graph, the data now appears as a smoother line which more closely reflects the force generated by the muscle. In sport and exercise, it is common to use EMG to identify precisely when a specific muscle is activated during a particular movement. For example, here we are recording muscle activity from the vastus lateralis and tibialis anterior muscles as Amy is cycling. In this case, the EMG shows that the vastus lateralis is active during the downward phase of the pedal cycle in order to extend the leg and push down the pedal. The tibialis anterior is silent most of the time, except when it is used for ankle dorsiflexion, pulling the crank back to the top of the pedal cycle. Sports scientists may also use EMG to measure muscle fatigue. If Paul holds a weight for a prolonged period of time, the EMG is initially stable, but then increases as he fatigues. He needs to recruit more and more motor units to maintain that force. This is just one way in which EMG changes during fatigue. But EMG has many other potential uses. In a clinical setting, it is used for gait analysis and the diagnosis of neuromuscular disorders. In my own research, I've used it to study the muscle activity evoked by reflexes. And the most cutting-edge developments even allow an EMG signal to control a prosthetic limb. Whatever the exact application, the assessment of muscle activity using elektromiography is clearly a very powerful technique in the world of sport, exercise and health.